Let's go back to an example that we talked about in the first week of class. And now we can apply everything that we've learned throughout the semester about the net worth of projects, about risk, and other concepts in order to determine whether or not the Port of Los Angeles should harden its terminals against extreme sea level rise. Remember, we had this setup where the Port of Los Angeles is going to upgrade its terminals soon in order to accommodate larger ships, new technology, and so on. They want to know, while we're upgrading anyway, should we harden the terminals against sea level rise at the same time in order to protect it against potential future flooding? What that means is primarily moving a lot of the electrical conduit and connections and elevating it so that if there is flooding or extreme storm surge in the future, then all of the electrical connections would be out of harm's way. They have to do these upgrade cycles every few decades, although it's uncertain exactly when that next upgrade cycle would occur in the future. And so the decision makers have two possible perspectives on this. One is that it's better not to risk it. There's a possibility that if we don't harden the terminals now, then if we start to see a lot of flooding in the future, then we will be forced to harden the terminals outside of the normal upgrade cycle. That would be really costly because it would produce more disruption to the operations of the port. And so that represents the risk in this example. One decision maker would think, let's not chance it. It might be a bigger initial investment now in present value terms compared to doing it in the future because of the discounting that occurs. But it's still worth it. We might think that the probability of seeing future flooding is sufficiently high that in expectation, the net present worth of the project would be worth pursuing it now instead of waiting and possibly having to do it outside of the normal cycle. On the other hand, another decision maker might think that the terminals are only vulnerable to really extreme sea level rise and storm surge, so they may think that the probability of having to harden outside of the normal upgrade cycle is sufficiently small such that the net present value of waiting would be the preferable option. In that case, it would be okay to wait and harden against sea level rise at the next upgrade cycle several decades into the future. Knowing what we know now, we see that both of those options, hardening now or hardening at the next future upgrade cycle, are both cost alternatives. Therefore, if we're thinking about a net present value associated with one decision versus the other, we're comparing them directly, and we're going to think about the benefit of doing this now as being the avoided costs of having a reactive response in the future. We're thinking about hardening now as our baseline for comparison. If we do that, there's a chance in the future that flooding will become so frequent that we're forced to react to it and harden outside of the normal upgrade cycle before we get to the next one several decades from now. That would be an extra cost imposed by these external climate change conditions. And that's what we want to avoid. That's what we're going to frame as our benefit when we're comparing the two projects. But really, we could also be framing this as each decision has a cost in expectation, and we can compare what's the present value of the costs associated with both options. And because they're cost alternatives, we want to minimize costs. And so then we would take the one with the smallest present value of costs. What we'll assume about the future is that if we act now, that we won't have any problems in the future. We are assuming that our response today is going to effectively mitigate the risk of having a reactive future response to sea level rise in the future. However, if we wait and roll the dice, then we have two possible outcomes. Either when we roll the dice, we get lucky and find that there's no extreme sea level rise, in which case there is no additional reactive costs. We don't have to take further action. We can make it to the future upgrade cycle in a few decades, and so there's no extra cost associated with that. However, if we get unlucky and experience extreme sea level rise, then we have this really large cost of hardening before the next upgrade cycle occurs. The paper that this example is based on is up on Blackboard, and just like the case study assignment that you're working on, the present value calculation has a number of parameters that go into the economic model that determine the worth of the project. When dealing with risk, we can think about parameters that influence the hazard, the vulnerability, or the consequences of how the port could be affected by storm surge and sea level rise. On the vulnerability side, they looked at the lifetime of the terminal, of how long can they go before the next upgrade cycle is required. The longer the lifetime of the terminal, the higher risk of having to harden outside of that normal upgrade cycle because you've got more years of sea level rise that could cause flooding. They also found that there's a parameter describing the level of flooding that triggers a reactive response. And this is really a subjective parameter that the decision makers have to decide about. How frequently can it flood before we throw our hands up and say, enough is enough? We have to harden the terminals now, even though it's not in our normal upgrade cycle. So that's related to the risk tolerance of the decision makers. On the hazard side, things that the decision makers can't control really is the size and timing of sea level rise. How quickly is the sea level going to change over time? The faster sea levels rise, the more risk of flooding, as you might expect. And then similarly, increases in future storm surge, whether or not storms become more frequent or more intense in the future. That would also influence the risk. So they can plug in these parameters, as well as some others, like a discount rate, for example, into their economic model and use that to calculate the value of hardening at this next upcoming upgrade cycle. We can graphically illustrate the decision as well as the potential future outcomes of those decisions using what's called a decision tree. In this diagram, the square represents the place where we have to make a decision that defines which alternative to take. Either we can harden now or we can wait. Each of the circles indicates a chance node of some uncertain event occurring in the future. So this is where we branch out into different possible outcomes depending on each decision. The economic parameters that are listed are L, the lifetime of the terminal, D, the discount rate per year, and tau, which is the year in the future at which point flooding could become so frequent that it forces that reactive response. If that happens before the useful lifetime of the terminal is up, that means tau is less than L, and we have a future reactive response that's been forced, meaning we incur extra costs. If we look at the upper branch of the decision tree, where we decide to harden now during this upgrade cycle, then we have one possible outcome, because we've assumed that with certainty, we can mitigate the risk and avoid a future reactive response. Therefore, the cost associated with that decision is only the cost of hardening. If we don't harden during this upgrade cycle, then we run into this chance node where we branch out into two possible future outcomes that could occur. On the lower branch, this is where we've gotten lucky, where no flooding starts occurring that forces a response before the next upgrade cycle, in which case we don't have any extra cost imposed between this alternative or the alternative where we wait until the next upgrade cycle. However, we said there's some probability that flooding will force a reactive response at time tau that's less than L before the next upgrade cycle. If that happens, then we have two different types of costs that occur. One, we have to harden the terminals. And so we have this C sub harden that's multiplied by e to the minus d tau. That is just a discount factor. In this paper, they used continuous compounding, and so e to the minus d tau is effectively just a p given f conversion factor. That's the formula for continuous compounding at a discount rate of d, where n, the number of years or the time, is equal to tau. However, we also assume that if they have to harden, they would go ahead and make the next upgrade anyway. Therefore, they're losing some of the value associated with the upgrade that they performed now because they're losing the end of that upgrade cycle's lifetime, and they have to make the next upgrade early. This L minus tau over L term just tells us what proportion of the lifetime of the current upgrade cycle is effectively lost by chopping it off the end when you are upgrading early the next time. Now we've enumerated the cost associated with each of the different possible outcomes for each decision. That means we can go back to our net present value calculation and plug in these numbers along with the probability of seeing different outcomes. Therefore, the expected net present value of acting now is the benefits in expectation of avoiding that reactive future response minus the cost of acting now. So we have P, if that's the probability of seeing a reactive response, times C sub 2 plus 1 minus P times C sub 3 minus C1. That leads us to this expression down below, and if that value is greater than 0, then we would say that acting now is justified because it has a positive net present value relative to waiting. I'll emphasize, though, that we don't necessarily know what the value of P is. We also wouldn't know what tau is. So decision makers are going to look at this equation and say, well, in this case, I ought to do a break-even analysis to figure out what combinations of the probability of a reactive response and when that reactive response would occur lead to acting now being justified. If they do that break-even analysis, they may arrive at the conclusion that their beliefs about the probability of a reactive response being needed is always greater than the break-even value, in which case they can be pretty confident that they would be making the right decision to act now.